So this is the system functional. All right, you could write it this way. And the next thing we want to do is find the impulse response. Okay. Now, to find the impulse response, basically you want to expand. And to expand, first of all, you should do long division. All right? Or that's one way to do it. All right. So if I want to, I should reduce this so that the order of the numerator is less than the order of the denominator. So we'll first do long division. All right. Now the numerator here, if I arrange that, that's actually r cubed over 3. And then I have, I'll just say plus 0r. And then I have plus r. Plus 0r squared plus r. And I'm dividing that by 1 plus r over 6 plus r squared over 3. Okay? So my first term is, this is kind of compressed here, but I think we can make this work. This is going to be r, so I'm going to subtract r cubed over 3. And then this is going to be, let's see, this is a r, so that's going to be r over 6. Yeah, it's just the same thing. Plus r squared over 6. And then it's going to be plus r. Is that right? Yeah, that's what I have here. So then what I have here left is, this subtract gives me 0. This subtract gives me minus r squared over 6. And this gives me a 0 here, because that's subtracting. All right. So then I'd have to do this one. I'd have to do plus 1/2. Or minus 1/2, rather. Minus 1/2. Or minus 1/2. Okay, good. All right, so then if I do minus 1/2, that's going to give me minus r squared over 6. And then this is going to be minus, let's see, r over 12. And then it's going to be minus 1/2. Okay. So this is going to give me a 0. Then the minus gives me r over 12. And then the minus gives me 1/2. Okay. So I could rewrite my impulse response if I wanted to. I have the integer part, which is r minus 1/2. So y over x is equal to, what did I write again? Here, let's squish it like this so we can see. It's equal to r minus 1/2. Sorry. And then I have plus what's left over, which is the r, looks like I could write this as r over 12 plus 1/2 divided by this stuff here, which was, let me write it the other way around, r squared over 3 plus r over 6 plus 1. Okay, just need to make sure that that's all right. Yeah, that denominator looks correct because the denominator checks out with this up here. Then I have my r minus 1/2, and then I have my remainder here. Let me just double check this term because I'm a little bit suspicious here. I took the minus 1/2 here, so I multiplied minus 1/2, minus 1/2, minus 1/2. And then subtract it, and then I get a positive. So I think I'm feeling pretty good about that. Okay, all right, so the next step is to expand this out. But actually, well, I shouldn't just expand this out, I should do partial fractions. So the next step is partial fractions. That's what my next step is. So how does partial fractions work in this case? Well, we've got that polynomial in the denominator, so we want the roots of this denominator, which is r squared over 3 plus r over 6 plus 1. All right, so let's not be afraid of complex numbers here. So we're going to look for negative b, which is 1/6, plus or minus the square root of b squared, which is going to be 1 over 36, minus 4ac, which is going to be 4/3. And then we divide that all over 2a. So that's going to be divided by 2/3. Okay. All right, so let's see what I'm going to do here. So I can flip up the 2/3, so that's going to be 3/2 times minus 1/6 plus or minus. Now we're going to have to put this over a common denominator. The 36 is 3 times 12, so that's going to be 1 over 36 minus 48 over 36, so that's really not very good. So it looks like that's the square root of negative 47/36. Now I just came up with this problem just out of the top of my head, so I can't really expect it's going to turn out nicely. Did I do that right? It's 1 over 36 minus, multiply the 4 by 12. It does give you 48, so it's minus 47/36. So it is what it is. Okay, so if I put in the 3/2, that's going to be the 3 cancels, so that's going to be equal to minus 1/4 plus or minus. And then I can certainly take out the I. So the 3, when I put the 3/2 inside, it's going to become 9/4. So the 9/4 multiplying by the 36, well, the 9 cancels that 9 and the 36. So it looks to me like I'm going to get the square root of 47 over 16i. Okay. So those are my roots. Okay. So how do we rewrite that denominator that way? Well, I guess here, let me switch this down. Well, that means that r cubed, that means that r cubed, and I'm going to write this out. It's not r cubed, but I'll write 1/3 times r squared. Let's see, this is going to be plus r over 2, and then this is plus 3. Right? That all works correctly, and that's going to be equal to 1/3. And then here I write the roots here, so it's going to be times r minus 1/4 minus 1/4 is going to be plus 1/4, and then I can do plus square root of 47/16i, and then it's going to be times r minus 1/4, r plus 1/4 minus square root of 47/16i. Okay. All right. So what we have here is this result here, this r to the 1/12 plus 1/2. Let me make it small so I can see it. So that means that r to the 1/12 plus 1/2 over the denominator, which is r squared over 3, and then plus r over 6 plus 1. It's going to be equal to something. I can write this as a over r plus 1/4 plus square root of 47/16 I plus b over r plus 1/4 minus square root of 47/16 I. Now there are different ways to do partial fractions, but I think the best way is like this. Do the cross multiply on the right hand side, and you'll get here, sorry, the color changed. Keep the same color. You get r over 4 plus 3/2. And then actually, I don't need to worry about the denominator because the denominator is the same on the left and on the right. Okay. So if I do the cross multiply here, that's going to be a times the denominator on the b term which is r plus 1/4 minus square root of 47/16 I. Then I have plus b times the other side, r plus 1/4 plus square root of 47/16 I. Right. Now the way to get these more right away is to notice that when r equals this value, when r equals this root, then the a coefficient goes away and you just get b. Right. Similarly, when this coefficient is equal to 0, when r plus 1/4 blah is equal to 0, then the a goes away and you just get the b. Right. So I'm just going to set r equals negative 1/4 plus square root of 47/16 I. If you don't know this way of doing partial fractions, it's by far the simplest way. So if I set r equal to this value and then evaluate that on both sides, I will get b directly. Okay, so that gives me, so that's going to give me minus 1/16. I'm just plugging in this value of r into this expression here. Minus 1/16 plus 1/4 the square root of 47/16 I. Okay, plus 3/2 is equal to, now this term is 0, and then I get plus b times, and then I take r, which is the minus 1/4 plus square root of 47/16 I. And you can notice that the minus 1/4 is going to cancel the plus 1/4, and I just get two factors of this. All right, so that actually gives it to me. That gives me b. So b equals, I'll just simplify a little bit. This here is going to be the minus 1/16 plus the 3/2. Well, 3/2 is how many 16ths? So I'll have to do the 16th here. So it's minus 1/16 plus, and then the 3/2 is going to be, I'm going to have to multiply this by 8. So that's going to be plus 24 in the 16th. And then I get plus, and then actually I could put this in the bottom. The 16 I can take out and just make that a 4, so that's going to be over 16 square root of 47 I. So that's the numerator, and then the denominator is going to be 2. I could take out the 16 here, and that's just going to become 1/2 square root of 47 I. Okay. Now it turns out that the value of a is easy to find. If I set r equal to the complex conjugate, okay, then I can do the same argument. All right. Then I would actually get the complex conjugate of this equation equal to a. So I'm going to get the complex conjugate of equation. Okay. So that means that a is simply equal to the complex conjugate of b. Okay. Now my answer, I'm just going to leave it as b for now, just because this is not so bad. I can write this out because the square root of 47's cancel. So this gives me minus 23 over 16, and then I have the 1/2, so the 2 comes on top, so that's going to be 2 over square root of 47 I. I can write it that way. And then here we got a lot of cancellation, and you get plus, well, you get the 1/16 divided by the 1/2 gives me 1/8. And then the 47's cancel, so that becomes plus 1/8. Okay. All right. So in summary, I get b equal to, if I can simplify this expression here, that looks like minus 23 over 8. Actually, when I pull the I up to the top, the I will become a minus I, so this is going to be a plus. It's going to be plus 23 over 8. You pull the I up to the top, so that's going to be square root of 47 over 47. If I'm going to rationalize the square root, and then I'm going to have the I on the top, and then plus 1/8. Okay, so that's my b, and then a is equal to b conjugate. Okay. All right, so finally, to get the impulse response, we have to write out. Okay. What we had was the system functional. Go back to what the system functional was. Let me just copy this. Okay. System functional. And I write it out in terms of R and I expand. Okay. Okay. So it's going to be equal to, and I'll just leave the B in just to make it, because you can substitute in the B afterward. So this is going to be equal to R minus 1/2, and then plus, so what was it? It was A, I forget what the two roots were, R minus something, and B, sorry, I was going to write that as B conjugate. It's B conjugate. Well, here I'll just write this for now as R minus alpha, because I know it has some root. And then this is going to be plus B over R minus alpha conjugate. Now I'm just going to leave the alpha and the B in and fix it afterwards. I think it will be easier to write. Now I want to expand this out in powers of R. Okay, so right? That's the key to finding the impulse response, because the powers of R become delays. Right? Now, so in order to do that, I want to write the denominator as, well, 1 over, and then I want to have 1 minus something, because then I can use the 1 over 1 minus x expansion. Which I know is equal to 1 plus x squared, and so on. All right, so how do I do that? Well, I've got the R minus 1/2. I guess I'll write that as minus 1/2 plus R. It's better. So I have y over, I'll repeat my y over x is equal to minus 1/2 plus R. Now, if I want to rewrite this as 1 minus something, I want to make the alpha into a 1 term, and I want to make the R into the something. All right. So if I want to do that, I'll have to divide top and bottom by alpha. So I'll take beta bar times 1 over alpha. Sorry, minus 1 over alpha, because I want to change the minus to a plus also. So I multiply the bottom also by minus 1 over alpha. Okay. And over here, what I want to do is I'm going to take the B, and I want to multiply this by minus 1 over alpha bar. And then this is going to be minus 1 over alpha bar down here. Okay. So let's see what we got here. So we have equal to minus 1/2 plus R. And then let's see, we've got a minus, so I'll take the minus outside here. Minus, and this is beta bar over alpha divided by, now when I divide this out, the minus 1 over alpha and the minus alpha gives me a 1. And then the other term is going to give me minus R over alpha. Right? Then this term is actually just the complex conjugate of this term. So that's going to be, again, a minus times beta B over alpha. And then divide by, this is going to be 1 minus R over alpha bar. Okay? So what I get in terms is minus 1/2 plus R, and then here I'm going to have minus, I suppose I can just take beta hat over alpha, and then this is going to be 1 plus R over alpha plus R over alpha squared plus dot 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 minus B over A times 1 plus R over alpha bar. Wait a minute, this should be alpha bar here, 1 over B over alpha bar, plus R over alpha bar squared, plus dot dot dot. Okay. Now I want to group like powers of R. So the first power, the constant is minus 1/2. Then I have minus beta bar over alpha, and then this becomes minus b over alpha. I keep saying beta, I mean b. I'm writing the right thing. I'm saying the wrong thing. Okay. All right, so you have all this stuff, and then we're going to have plus, and then we have here we have the r. So r from the first term gives me a 1. Then this becomes minus, looks like beta bar over alpha squared. And then this one here looks like the complex conjugate of that, minus beta b over alpha bar squared. Okay. Then the terms become more regular. I have r squared. The r squared term is going to be just going to have the beta hat over alpha, b hat. Now I'm going to have an alpha cubed. And it's going to be a minus. Sorry, this is going to be a minus. So let's put that in. It's going to be a minus r squared. And this is going to be b over alpha cubed. And this is going to be plus, sorry, b bar over alpha cubed, plus b over alpha bar cubed. Okay. And then you can kind of see that pattern here. It's going to be minus, if I take r to the n, any tower n, I'm going to have a b hat, beta conjugate, divided by alpha. Now the power down in the denominator is 1 more than the power up there. So I'm going to show that. So that's going to be alpha, the n plus 1. And then this is the complex conjugate, b over alpha bar, n plus 1. Okay. And minus dot dot dot. Okay. All right, so that actually gives me the impulse response. So to get h of n, just take the coefficient of r to the n. That's all. Okay. Sorry, didn't copy r to the n. Still didn't copy. The coefficient of r n in the expansion. Doing kind of weird things. Okay. All right. So we could write it this way. We can say h of n. So we have cases here. So we have h of n is equal to 1 when n equals 0. Sorry, it's not equal to 1. What am I saying? H of n is equal to minus 1 over alpha. Well, minus 1/2, sorry. Can't read my own writing. That's a 2. Minus 1/2. Then I'm going to have minus b conjugate over alpha minus b over alpha bar. And that's when n equals 1. Then, no, that's when n equals 0, sorry. Then when n equals 1, I'm going to have cases here, so let's move it down. N equals 1, I'm going to have the coefficient of r, which I can pull off right here. That's h of 1, so that's going to be 1 minus alpha squared, and then minus b over alpha bar squared. N equal 1. Okay, and then I have to extend this down, and then I'm going to have, and then this is going to be plus b over alpha bar n plus 1. And this is for n greater than or equal to 2. Okay, all right, and if you're going to do solution like this, which you can, in fact, this is a good way to do it, because if you program this on the computer, this is how you would do it. You would use these variables to hold complicated expressions. So this is actually a good way to do it. I have my value of b. My value of b was up here somewhere. It's right here. I think I can simplify it. Well, I'm just going to grab it. I don't want to carry. So it's really a lot simpler that I just write b instead of carrying this down all the way in all of my expressions. So I do recommend that you do that. Okay. and it looks like this. I'll pull it up. Whoops, didn't catch. So B is this, and then my alpha is equal to, it doesn't have the pen. Let's get the pen back. Pen's here. My alpha is equal to, I know I have that somewhere. Let's go ahead and find it. Yeah. Alpha was the root. So which root was it? I think alpha was the root attached to B conjugate. So let's see. So alpha conjugate was the root attached to B. So let's see. So, all right. So it looks like alpha is this here. Alpha is this here. So I'm going to. It's actually the negative of this, right? Because there's a plus here, so it's the negative of this. So it's the negative of this value, right? Because that was the value under the A, and the A was B conjugate. So I'll copy this, and I'll move it here. So there are advantages and disadvantages to having this software, but I do enjoy just being able to copy. Okay, and let me not forget to put a minus here. Okay. Now I did this quite quickly, so it's quite possible I did make a algebra mistake somewhere, and it's not easy to check. So if you work through this and find a different answer, let me know and I'll correct my video. But I'm hoping that you can see the general process here. So let's review the general process. General process was we take the system. Well, we did the system diagram we did in the last video, and I went through that in detail. We took the system functional. First thing we did was we did long division so that the degree of the numerator was less than the degree of the denominator. Right? There are other ways to do that, but do you want to do that? You want to split that out. Then you expand this. Then you expand this part in partial fractions. Partial fractions, you know what the two roots. You find the two roots of the denominator, which are here. And we got the two roots. And then we know that the expansion will look like this. It will be a over the first, or r plus r minus the first root, plus b over r minus the second root. Right. Notice the roots here are the negatives of these values. Right. And then we go ahead and write this out. Then you cross multiply. You cross multiply, and then you simply set r equal to one of the roots. And the equation then simplifies on both sides, and you can find one or the other of the coefficients. In this case, the coefficients are complex conjugates of each other because the equations that you get are complex conjugates of each other. Finally, to get the impulse response, I write the denominators as 1 minus something. All right, I had to multiply top and bottom to make that happen. Okay. And once you have this expansion 1 minus something, you can expand it out in the power series. All right. So the steps are pretty logical. There's some time to compute, and you have to keep your calculations organized, but that's the general idea of how you do it. Okay, hope you enjoyed this video.